All right, so now we see an example of a function. Disregard this for now. We see an example of a function that basically is not split up into this sum of functions of s that we could easily look at the table and just figure out the Laplace transform or the Laplace inverse transform of. And so what we need to do is we need to re-represent this function in a form that is nice and that we can use linearity and go back and use the Laplace transform table so that we can actually get the function of t that we're after. Okay, and so how we do that is we use something called partial fraction expansion. Partial fraction expansion basically says that, I have these three terms in my denominator. I have s plus 1, and s plus 3, and I can represent this entire function as a sum of what are called partial fractions, where each fraction has a denominator which is one of these three terms. Okay, so s for the first term, s plus 1 for the second term, s plus 3 for the third term in this case. And those three terms have coefficients. These are integer values here that we can find, and this partial fraction expansion will be equal to our original function. But then you'll see that each one of these individual terms is now being added due to the partial fraction expansion rather than multiplied. And now this would be really easy to take the Laplace inverse transform of each individual term using linearity. So that is why we need to be able to perform partial fraction expansion. The challenge of partial fraction expansion is determining these coefficients, okay? And we can actually do that really easily. It's not that challenging. And so let me show you how we do that. So the way that we do that, so we need to determine A, B, and C basically. The way you would start with a problem like this is you would say, oh, okay, I have this function of s here. I know it's ugly, I can't transform it, and so what I know I can do is I can rewrite it as a sum of partial fractions. You could call this a1, a2, and a3 if you wanted to. These are literally just variables, and once you determine these three values here, then you've completed the partial fraction expansion, and then you're able to use the Laplace inverse transform table. Okay, so let's go ahead and start finding these coefficients. Let's start with a. So the way that we do this is we first multiply. Here, let's, I may or may not need more space here. Did I give myself? No, I didn't give myself 2 slides. Let's see. If I need another slide, then we'll do that. But let's start by copying. Let's take 3 copies of this. I'll take a screenshot, and then I'll copy it. I'll copy it here. I'll do it here. Here, it keeps changing the size on me. There, and let's do one more. I can just paste the original one. And a little bigger, that's fine. Okay, so these 3, because we need to find A, B, and C, so we basically need to do this 3 different times. And so what we're gonna do here is in order to find A, we take the denominator of A and we multiply both sides by that denominator. So here we're going to multiply both sides by s. And what you'll notice is what that does is it allows us to cancel the s on the left side and the s on the right side as well with the term that we're after. So here we're after A. So let's just put A for this one, B for this one, and C for this one. So the first thing we do is we multiply both sides by the denominator for that term. And so that would end up with an s here and an s here. And then, so let me rewrite both sides now. I have s squared minus 4s plus 3 divided by, actually I could factor that too. That's going to be s minus 1 times s minus 3 divided by s plus 1 times s plus 3 because I canceled the s. And that's going to be equal to A plus bs over s plus 1 plus cs over s plus 3, okay? And now what we do is we evaluate at s equals 0. Evaluate both sides at s equals 0, okay? Why do we do that? Well, we do that because that gets rid of the b and the c terms, so all we're left with now is A, right? So a is equal to this left-hand expression when s is 0. So I can, okay, s goes to 0. I get -1 times -3 gives me 3. On the bottom, I get 1 times 3 gives me 3. So for a, I just get a value of -1. It's really just that simple. So that's my value for a in my partial fraction expansion, -1. Okay? I actually think I did something wrong here. Yeah, -1 times -3 gives me a +1. Okay, so it should be +1. Sorry. +1. A equals 1. Sorry. End up trying to go too fast, and then you just keep making mistakes. That just looks so ugly. All right, that's fine. So now let's do the next term. Let's do b. So for b, all we have to do is the same thing. We multiply both sides by the denominator of b, so it's s plus 1 on both sides. You'll notice that cancels the s plus 1 on the left side. It cancels the s plus 1 on the right side. And then, so what we would end up with here is s minus 1, s minus 3, over s times s plus 3. And that's going to be equal to a over s multiplied by s plus 1 plus b plus c over s plus 3 times s plus 1. And what do we have to do? We have to evaluate both sides at s equals -1. Why s equals -1? Because that's the value that causes this a and the c terms to go to 0, right? If I plug in a -1 here, that goes to 0. So this goes to 0, this goes to 0, and all I'm left with is b. So b is going to be this expression evaluated at s equals -1. Pretty straightforward. So I say -1 on right here. That's -1 times 2 on the bottom gives me -2. The top is going to be -2 times -4 is 8. So 8 over -2 gives me -4. So b is going to be -4. And so -4 is my value for b in my partial fraction expansion. Okay, I'm going to go ahead and end this video here because I think it's probably gotten a little bit long, but we'll wrap this example up by doing part C and then writing out the final partial fraction expansion in the next video. Hopefully you're starting to see the process here, but it's pretty straightforward. So we'll do a little bit more of it in the next video when we wrap up with C, finding C, and then we will do some example problems where we have to use the partial fraction expansion to solve our problem, okay? So I'll end the video here and we'll see you guys in the next one.